Moving on into Module 6.3, we're going to be talking about data integrity constraints and many of our types of keys, including superkeys, candidate keys, key attributes, non-key attributes, primary keys, and alternate keys. We're going to talk about the entity integrity constraint, the referential integrity constraint, and the foreign key constraint. Data integrity constraints are rules that govern the behavior of data in a database, and these are simply technical expressions of the business rules that we've talked about already. And they are considered to be a part of the schema and are going to be maintained across the conceptual, external, and internal schemas. Now, in talking about the concept of unique identifiers, we have to talk about superkeys, candidate keys, the primary key, and alternate keys. Superkeys are a set of one or more attributes which, taken collectively, uniquely identify a tuple of a relation. It has the property of uniqueness. And we already said that in a relation, every tuple must be able to be uniquely identified. So by virtue of that fact, the collection of every attribute in the relation is necessarily going to be a superkey, right? So for you as a student, this collection of attributes like your first name, your last name, your hair color, your eye color, and your PeopleSoft ID, all taken together would be a superkey, because with those 5 attributes together, you can be uniquely identified, right? You could also be uniquely identified by a subset of that, like your first name, your last name, and your PeopleSoft ID, right? Not needing your hair color and your eye color. Or maybe even just your first name on your PeopleSoft ID, or just your PeopleSoft ID. All of these collections of attributes would be considered a superkey as long as they can uniquely identify you. Now, going one step further, a candidate key is a superkey with no proper subset that uniquely identifies the tuple of a relation. So we have the property of uniqueness and the property of irreducibility. Okay, this set of attributes will not be unique if we reduce it any further. Okay, so going back to the example of a student and something like PeopleSoft ID, first name, last name, hair color, and eye color being a superkey, well, that's unique, but it's not irreducible, right? Because we could take away the attribute of hair color and it would still be unique. I can uniquely identify you with PeopleSoft ID, first name, last name, and eye color. Right? I can also further reduce this by removing eye color and by removing last name and by removing first name, right? I can reduce this all the way down to PeopleSoft ID and still uniquely identify you. Now, at that point, I can't reduce any further and remain unique. We're down to just one attribute, PeopleSoft ID. So PeopleSoft ID would be a good candidate key. And note that we might wind up with multiple candidate keys or multiple combinations of attributes that uniquely identify you and are irreducible. Now, from this set of candidate keys, we're going to select one and only one to be our primary key. And a primary key is a candidate key with no missing values for the constituent attributes. So it has the property of uniqueness and irreducibility and the entity integrity constraint. And all the entity integrity constraint means is that we cannot have any null values. And then finally, an alternate key is any candidate key that we did not select as the primary key. So an alternate key is a candidate key that we did not apply the entity integrity constraint to. So let's take a quick look at an example of prescriptions for medications. So if you were to take a moment and really observe the data values here, you're going to find that this first attribute, prescription number, is unique. However, the second attribute, patient number, is not unique, right? We have some duplication of this value, 7642. We have some duplication of this value for 772. 7384 we see multiple times. Also note that medcode by itself is not unique. However, if we combine patient number and medcode, then these two attributes together are unique. And basically what this is saying is that each patient can only be prescribed a medication one time. Right? We're not going to have patient 7642 be prescribed penicillin multiple times. So these two attributes together are unique, and this dosage attribute really doesn't come into the equation, right? This is really either 2 or 3 all the way down the line. So this doesn't really have anything to do with being able to uniquely identify tuples in this relation. So again, note that a superkey is one or more attributes which together uniquely identify a tuple. So let's identify all the superkeys we have here. And first off, prescription number, which just by itself can uniquely identify a tuple. So that's going to be a superkey. Also, that a superkey plus any other attributes at all is also going to be a superkey. So prescription number and patient number together is a superkey. Prescription number and med code together is a superkey. Because if I know the prescription number and the medication, then I can use that to uniquely identify a tuple. Prescription number and dosage is a superkey. Patient number and med code we said is unique, so that's a superkey. Patient number, med code, and dosage would be a unique identifier, so that's a superkey. Patient number, med code, and prescription number is a superkey. Prescription number, patient number, and dosage is a superkey. Prescription number, med code, and dosage is a superkey. And then, of course, every attribute in the relation, prescription number, patient number, med code, and dosage, taken all together, would be a superkey. So we have a lot of superkeys in this relation. And generally, we can say if some set of attributes K is a superkey, then any superset of that set is also a superkey, right? Any set that contains this unique set of attributes K is also going to be a superkey. So superkeys uniquely identify a tuple, but there are going to be a lot of them. So why don't we do a little bit better and identify our candidate keys. So candidate keys, like we mentioned earlier, have the property of both uniqueness and irreducibility. It's a superkey that has no proper subset that uniquely identifies a tuple. Okay, so prescription number, for example, is a candidate key because we can't reduce that any further and it still be a unique identifier. In fact, we can't reduce that any further at all because it is an atomic attribute. Now, prescription number and patient number taken together is not a candidate key because the proper subset, just prescription number, is a unique identifier, right? This is not irreducible. We can reduce this set of two attributes and it maintains the property of uniqueness. Same for prescription number and med code. We can reduce this and it remains unique. Prescription number and dosage, same thing. We can get rid of dosage and prescription number is still unique. However, patient number and med code together is a candidate key because if we get rid of med code, patient number does not uniquely identify every tuple in the relation. And similarly, if we got rid of patient number, med code does not uniquely identify every tuple in the relation. So this is unique and irreducible, therefore it is a candidate key. Now when we add dosage, this is not a candidate key because this is reducible. We can remove dosage from this set of attributes and still uniquely identify every tuple in the relation. Okay, same for patient number, med code, and prescription number. And in fact, this is reducible in two different ways. We could either remove the prescription number and uniquely identify every tuple using patient number and med code, or we could remove patient number and med code and uniquely identify every tuple based just on prescription number. Okay? And then similarly for these last three examples, they're all reducible because we can reduce this down to just prescription number or just patient and med code. Now, another thing that we need to understand about uniqueness is that attributes are always going to be either a key attribute, a non-key attribute, or a candidate key. Okay, and this is going to be very important when we start talking about normalization in a couple of lectures. So a key attribute is any attribute that is a proper subset of a candidate key. Okay, and one important thing to note when we're talking about set theory is that a set is a subset of itself, but is not a proper subset. Okay, so if we have a set of attributes, A, B, and C, the entire set, ABC, is a subset of ABC, but it is not a proper subset of that set. Okay, so the proper subsets of the set ABC would be A, B, C, AB, BC, and AC. Okay, so those would be our 6 proper subsets of the set ABC. Okay, so a key attribute is any attribute that is a proper subset of a candidate key, and a non-key attribute is any attribute that is not a subset of a candidate key. So now going back to our prescription example, we had identified these 2 candidate keys for the relation prescription number and this composite candidate key of patient number and med code together. Okay, so we said every attribute must be either a key value, a non-key value, or a candidate key. So prescription number is a candidate key because it is not a proper subset of a candidate key. It is a candidate key itself, and it is not a subset of a candidate key, right? Patient number is a proper subset of a candidate key, therefore it is a key attribute. Similarly, med code is a proper subset of a candidate key, so it is a key attribute. But dosage is not a subset of a candidate key, so it is a non-key attribute. Now, prescription number is a subset of a candidate key because prescription number is the candidate key and prescription number is a subset of that set of one attribute, prescription number. But the definition of a non-key attribute is that it is not a subset, okay? So all of our attributes are going to be one and only one of these 3 things: a candidate key, a key attribute, or a non-key attribute. And like I just mentioned, candidate keys themselves are not key attributes because a set is not a proper subset of itself. Our primary key is a candidate key with one additional constraint: it must not be missing, or it must not be null. And we call this having the entity integrity constraint. So we have these 2 candidate keys, prescription number and the combination of patient number and med code. Which should we choose? Well, technically it doesn't matter. Both would be equally valid. But from a functional perspective, we probably want to choose the one that's going to be a little bit easier to interact with, and importantly, the one that will never be null. So in this case, I would probably choose prescription number, but either one of the candidate keys would be equally valid to use because I don't think we would ever have a prescription that doesn't have both a patient number and a medication on it. So those 2 things together would probably be fine to use. And then any candidate key that we do not select to be our primary key is going to be an alternate key. All right, so now we have another example. This looks very similar to what we did before, but we've changed up the data just a little bit. And what I'll point out to you here is that prescription number is no longer a unique identifier, right? We have some duplication of these values like B100 and B102, so this is not unique. And from the business rule perspective, what this says to me is that in the previous example, every prescription had to be for a single medication for a single patient. But now we've kind of changed the business rules to say that we can write a single patient, a single prescription that has multiple medications on it, okay? And we see this play out in the data such that this combination of patient number and med code is unique, and the combination of prescription number and med code is unique. So while we can write multiple medications on a prescription, we could not have the same medication written on one prescription more than once, right? So we have 2 composite unique identifiers: patient number and med code and prescription number. So let's go through and identify our super keys. Of course, patient number and med code, that's going to be 1. And so now any superset of this super key is also going to be a super key. So patient number, med code, and prescription number, patient number, med code, and dosage. Also, we have the unique identifier of prescription number and med codes. So all of the supersets of this super key, like prescription number, med code, and dosage. And then, of course, all of the attributes taken together must be unique: prescription number, med code, patient number, and dosage. So of these 6 super keys we've identified, which of these are candidate keys? Or which of them are irreducible? Which of them can we not remove any attributes from and they still maintain this property of uniqueness? Well, patient number and med code, we know med code by itself is not unique, and we know patient number by itself is not unique. So this is irreducible. It is a candidate key. Now, patient number, med code, and prescription number is reducible because we could get rid of the prescription number and still uniquely identify all the tuples. Okay, same for if we add dosage. Prescription number and med code taken together is unique. However, if we get rid of the prescription number, med code is not unique by itself. And if we get rid of the med code, prescription number by itself is not unique. So this is a candidate key. It is irreducible. If we add dosage, of course, that is a superset of this candidate key, and thus it is reducible, so it is not a candidate key. And this collection of all four attributes in the relation would be reducible either to just prescription number and med code or to just patient number and med code. So this is not a candidate key. So we identified two candidate keys for this relation, patient number med code and prescription number med code. And there are four atomic attributes in this relation: prescription number, patient number, med code, and dosage. And recall that we said all of these attributes are going to be one and only one of our three possible things: a candidate key, a key attribute, or a non-key attribute. So prescription number is a proper subset of this candidate key. Therefore, it is a key attribute. Patient number is a proper subset of this candidate key, so it is a key attribute. Med code is a proper subset of both of our candidate keys, so it is a key attribute. And dosage is not a subset of any of our candidate keys, so it is a non-key attribute. So in this case, we do not have any atomic candidate keys. All of our atomic attributes are either key attributes or non-key attributes, and both of our candidate keys are composite candidate keys. So here is just kind of a synopsis of all of the possible combinations of attributes and whether they are a super key or a candidate key. And one thing that I would point out here is that this is kind of a stepwise progression in that all of our candidate keys are always also super keys. But the opposite is not true. Not all of our super keys are candidate keys, right? Because in order to be a candidate key, you must be a super key. In order to have both the property of uniqueness and irreducibility, you have to first have the property of uniqueness, which is what super keys have. Moving on to our referential integrity constraint, I would like to point out that our key constraints, like being a super key or a candidate key, and the entity integrity constraint, meaning that we cannot have any null values, pertain to individual relations. Our referential integrity constraints are specified between two relations. Specifically, the referential integrity constraint is used to enforce consistency across tuples of two relations. And we can kind of informally say that a tuple in one relation that refers to another relation must refer to a tuple that exists in that relation. Okay, and this kind of makes sense. If a tuple in one relation is going to refer to a tuple in another relation, it must be referring to a tuple that exists. Then to take this one step further, we have the foreign key constraint, which establishes an association between two relations and maintains the integrity of that association. So for the foreign key, we say an attribute or set of attributes in one relation, we're going to call this set of attributes A2, shares the domain with some candidate key, we're going to call that attribute or set of attributes A1 in another relation. And when that occurs, we say that that original set of attributes A2 is said to reference or refer to the relation schema R1. And we refer to this as inclusion dependency, and we write it like this. We say that attribute A2 in relation R2 is inclusion dependent, and that's what this little symbol here means, on the attribute or set of attributes A1 in the relation R1. So this attribute is inclusion dependent on this attribute, right? Or said another way, all values of this attribute R2.A2 must be in the domain of values of this attribute to which it refers R1.A1. To illustrate this, let's take a look back at our Bearcat model and this relationship between plants and projects, because we're pretty familiar with this at this point. We say plants undertake a minimum of 0 and a maximum of many projects, and projects are undertaken by a minimum of 1 and a maximum of 1 plant. And in this case, plant is the parent and project is the child, and we're going to put the foreign key in the child entity. So that's what this project underscore plant number is a foreign key that refers to a candidate key and typically the primary key in the relation to which it refers. So now all values of this attribute are in the domain of values of the attribute to which it refers, right? So all values of this foreign key must be found in the set of values of the candidate key to which it refers. And that is currently the case, right? And this is what the foreign key constraint states, that whatever tuple this value refers to must exist, right? We can't have a value here that refers to a value that does not exist in this plant table that we are referring to. Okay, we can only have values 11, 12, 13, 15, 17, and 19. We couldn't say we have a project that's assigned to plant 25, because then that tuple would be referring to a value that does not exist in the domain of values of the candidate key that we're referring to. That would be a violation of the foreign key constraint and a violation of referential integrity. When considering which entity to place our foreign key in, the first thing we want to look at is the cardinality of the relationship. So in this case, we have a one-to-many relationship, and the entity that has the cardinality of many is going to be the parent. So in this case, because we're reading across the relationship, plant has a cardinality of many, so it is going to be the parent. And in this one-to-many relationship, we want to place the foreign key in the child entity. Okay, so we're going to place the foreign key in the employee entity. So for each employee, they have this attribute that we're calling plant number that indicates what plant they are an employee of. Okay. So this is a foreign key that refers to this candidate key, and in this case, the primary key, PL_NO, or plant number. So every value of this foreign key, plant number, must be in the domain of values of the plant number attribute to which it refers. Said another way, this must be a valid plant. If our plant numbers are 10, 11, 12, and 13, we cannot have an employee assigned to plant 9, for example. Now, would it even make sense to place the foreign key in the plant entity? Let's take a look at what would happen if we did that. So now we're going to take our plant entity and add an empID attribute that is going to refer back to the empID in the employees table. And what we find is that we've now had to duplicate the plant name and the budget for every employee that is assigned to that plant. So we wind up having a tremendous amount of data redundancy. However, when we correctly model this by putting the foreign key in the employee entity, we have no redundancy. So that's a much better solution. Now, in the case of a one-to-one relationship, it's a little bit different because there is no clear parent in the one-to-one relationship. We could consider faculty to be the parent, or we could consider department to be the parent. So in this case, we're going to put the foreign key with the entity that has total or mandatory participation, right? Because every department is going to have a faculty member that is the head of that department. However, not every faculty member is going to be the head of a department. Okay, so this would be the best way to model this. And if we were to put the foreign key in the entity that has optional or partial participation, in this case, we're not going to experience a lot of data redundancy, but we are going to be introducing a lot of null values for the foreign key. Okay, and generally speaking, null values are pretty difficult to work with in relational databases and can make things a little bit trickier and not really work as expected. So anything we can do in our design to reduce the number of null values is going to be helpful. And then, of course, there are a couple of fringe cases. For example, if both sides of a one-to-one relationship have mandatory participation, then it really doesn't matter which side you place the foreign key in. And I really kind of struggle to even come up with an example of when we're going to have a one-to-one relationship with both sides having mandatory participation, because generally then you would just want to have everything in one relation. But if that were to come up, then it's really not going to matter where we put the foreign key. And if we had a one-to-one relationship where both sides have optional participation, there's not really going to be a hard and fast rule about this, but I think you're going to find that it would generally be better to put the foreign key with the entity that has fewer instances, just because this is going to result in fewer null values. Now, another approach to this one-to-one relationship where both sides have optional participation would be to use a gerund to decompose that, and that would ensure that we have absolutely no null values. So that might be an option worth considering too. Now, keep in mind that we can have multiple relationships between two entities. For example, we have a relationship between faculty and departments in that one faculty member is head of a department. But then we also have a relationship between faculty and departments in that faculty members are a member of one department, but a department has many faculty members that are a member of it, whereas a department has only one faculty member that is head of it. So in this case, we have two foreign keys. In the faculty table, this department attribute is a foreign key that refers to department ID in the departments table. And then in the departments table, head is a foreign key that refers to the employee ID in the faculty table. Okay, so because this is a one-to-many relationship between faculty being a member of a department, we place the foreign key in the faculty table. And then in the one-to-one relationship where a faculty member is head of a department, we placed the foreign key for this relationship in the department table because it is the entity that has mandatory participation in this one-to-one relationship. Now, if we had messed up and done this the wrong way and put the foreign key for this member of relationship in the department table instead of the faculty table, what this is going to result in is a lot of redundancy because we're having to duplicate the department name and the faculty member that is the head of the department for every employee that is a member of that department. So this introduces a lot of redundancy and is just not the right way to model this. So that wraps it up for module 6.3, where we talked about superkeys, which have the property of uniqueness, candidate keys, which have the properties of uniqueness and irreducibility, key attributes, which are proper subsets of candidate keys, non-key attributes, which are not subsets of candidate keys, primary keys, which are candidate keys with the additional entity integrity constraint, or that they cannot have any null values, and alternate keys, which are simply candidate keys that we did not select as our primary key. The entity integrity constraint is the constraint that we apply to a candidate key to make it a primary key, and that just says that it cannot have any null values. The referential integrity constraint states that when a tuple in one relation refers to a tuple in another relation, the tuple that it is referring to must exist. And the foreign key constraint is just a special case of the referential integrity constraint, which says that all values of a foreign key attribute must be in the domain of values of the candidate key to which it refers.